You change the button on your checkout page from blue to green. Over the next week, conversions go from 4.1% to 4.9%. That's a 20% relative improvement. Do you ship it? The honest answer is that you cannot possibly know yet because you haven't asked the only question that matters. If the button color did absolutely nothing, how often would you see a gap this big anyway? Purely from luck. Everything called statistical significance is machinery for answering that one question. Today we build a hypothesis test from scratch with no formulas, no lookup tables, and no statistics library. We'll shuffle data to generate the null hypothesis directly, compute a p-value by counting, and then spend real time on what a p-value is not, because the standard misinterpretation is genuinely everywhere, including in published papers. The logic of a hypothesis test is a proof by contradiction, and it's worth stating plainly. You assume the boring explanation is true, that the button color has no effect at all. That assumption is the null hypothesis. Then you ask, if that were true, what range of results would I expect to see just from random variation? If what you actually observed sits way outside that range, the boring explanation starts to look inadequate. Traditionally, this is where a textbook hands you a t-statistic, some degrees of freedom, and a table to look up. And that works, but it hides what's happening behind machinery, and it comes with assumptions about your data being roughly normal that often aren't checked. There's a better way to learn it, one that requires no formula at all, and it also happens to be more robust. It's called a permutation test, and the idea is beautiful. If the button color genuinely has no effect, then the labels blue and green are meaningless. Every visitor's outcome would have been exactly the same whichever page they got. And if the labels are meaningless, we can shuffle them randomly and nothing should change. So let's shuffle them thousands of times and see what gaps randomness produces on its own. Here's the whole test. We pull every visitor's outcome, ignoring which group they were in. Then 10,000 times, we shuffle that pool, split it back into two groups of the original sizes, and record the difference between their means. Those 10,000 differences are the null distribution. Not assumed, not looked up, generated from our own data. Now the p-value is just counting. What fraction of those shuffled differences were at least as extreme as the one we actually observed? Run it, and we get 0.031, 3.1%. So if the button color did nothing at all, we'd see a gap this large about 3 times in 100. That's the p-value. It's a proportion of a simulation we ran ourselves. Here's the picture. This histogram is the 10,000 shuffled differences. Everything randomness produced when the labels meant nothing. It's centered on 0, which is what you'd hope. The amber line is our actual observed difference, out in the right tail. The shaded region beyond it is the p-value as an area. Small area, unusual result. Now, the definition everybody gets backwards, and it matters. The p-value is the probability of seeing data this extreme if the null hypothesis is true. It is not the probability that the null hypothesis is true. Those are different statements in the same way that the probability of a positive test given illness differs from the probability of illness given a positive test, which is exactly the Bayes problem from episode 3, wearing a different hat. Practically 3 habits. Decide your threshold before you look at the data, because choosing it afterwards is how you talk yourself into anything. Report the effect size next to the p-value, because with enough data, a completely trivial difference becomes significant. And prefer a permutation test when your data is small or oddly shaped. It costs you 100 milliseconds, and it makes no distributional assumptions. The honest caveat is bigger than usual here. The 0.05 threshold is arbitrary. It's a convention from the 1920s, not a law. And it creates a genuinely damaging incentive, because a result at 0.049 gets published and one at 0.051 doesn't, despite those being essentially identical evidence. There's an entire replication crisis downstream of treating that number as a bright line. A p-value is one piece of evidence, not a verdict. One sentence. A p-value answers how often luck alone would produce a result this extreme and nothing else. Next episode, we look at what happens when you get it wrong. Because there are two completely different ways to be wrong here. They trade off against each other, and every threshold you pick is a decision about which mistake you'd rather make.